Okay, so this is the second module in the basic neural network models, lecture 12. And now we're going to touch loss functions and also a very, very important layer called the Softmax layer. Okay, so we already covered the multi-layer structure, and so this just shows you a very simple, actually two hidden layer, a multi-layer perceptron with 3 inputs and 2 different outputs. So if I remember correctly, in the beginning of our regression session, their student asked, can we have multiple regression outputs? So in everything we covered in the linear regression and also the polynomial, although we have only one y output. But in fact, of course you can. You can have multiple y. That y, it depends on what you care. So in this case, there are two output variables. So when you have 2 output variables, how do you calculate the loss? So in this case, we just sum. So assuming you have the true y is a vector, just y1, y2. You have a predicted y, actually right here. And then you just compare them. And using summation of each and take a square and then sum over all the possible y dimensions. So this is my y truth, this is my y hat vector. So essentially this is just a sum of square error when you have y as vector outputs. Very simple. It's this different, gradient is also extremely easy to do the calculation. So almost the same as what we had before. The only difference is y, it's a vector now. All right, so that's the basic regression. And then let's come back to the classification. So we already covered many times is the classification is we just have a sigmoid here. So this sigmoid compression function essentially just modeled this p hat, treating this y as Bernoulli variables, and we use the cross entropy or the negative log likelihood as a loss function. Very simple and intuitive. And then the fundamental reason is we treat this as a Bernoulli distribution, so head and tail. And then in Bernoulli distribution, you only need one parameter, p head. After you have that p head, you can write down its probability as p to the y, and then 1 minus p, 1 to the y. So this, we actually did this derivation for the basic Bernoulli, and then it's very easy to extend that to the logistic regression version of Bernoulli. The only thing is you replace the p head into this p y equals to y conditional xi. Everything else is the same. Yeah. So, okay, so now if we have a multi-class, what should we do? So most important, we actually emphasize, right? We model the output. So everything we covered is in the family of base classifier. And especially in this section, they're all the discriminative classifier. So essentially, we need to be able to write PC conditional X. And then in this case, the C has many. So one from C1 onto CK. So I use 1, 2, 3, 4, 6. So this, I'm trying to give you just an intuitive think what's the differences. So if you still remember, so roll a die. So if you roll a die, dice, and this gives you 6 possible outcomes. So the probability of the 1 face you, the probability of 2 face you, until the probability 6 face you. And this is very similar to flip the coin, either head or tail, but in there are only two outcomes. But now we have 6 outcomes. And then this is called Martinelli distribution. All right, so then again, like base classifier, the most important is how can I get this py from the first possible outcome until the case of possible outcome conditioned on the x input. And they are essentially the Martinelli distributions parameters. So the reason why in a Bernoulli case we don't need to estimate two parameters is because the summation equals to 1, right? So when we know one of the parameter, we actually know the other. So that's the reason why we only need to estimate one of them, and then people just pick the p hat. Whatever you estimate, you just treat that as the p hat. Okay. All right. So when in the MultiClass case, how do you like, you need to have an x. How do you model that py equals to ck? So py equals to ck condition on the x. How do you estimate that parameter for that Martinelli distribution, right? So first is people normally give you, assuming like this type of labels. So assuming this is a label set, like this my C. So let me still use, let's use Y just to get it consistent. Oh, actually I use the G here, sorry. All right, so my output class variable is 1, 2, 3, 4. There are 4 cases, and there's no value relationship here, even though I use 1, 2, 3, 4. So keep that in mind. And I can also represent this maybe something else, right? I can also write this as a C variable. Maybe, let me think about, maybe I'm trying to classify the newsletters into different class. So is that about politics? Is that about finance? Is that about health? Is that about maybe entertainment? And this give me, let me try to make it 5 just to let you get a sense of entertainment. Then there should be a technology. Yeah, so this actually in the first case, k equals to 4. In the second case, k equals to 5. This is the size of the class space. All right, so in both cases, you actually convert it into k basis vector representation. And for the first y1, if it's 3, so in this case, this was like the first example was labeled as class 3, and then my vector is 0, 0, 1, 0. So this is size 4, k equal to 4 because, and then only that third class it has a label 1. Everything else as 0. So this is what we meant basis vector representation. People sometimes also call this one hot representation. So maybe one hot is easier to memorize. So there's only 1 in my k size vector, binary vector is 1. So this is how we normally represent this kind of discrete variables. All right, so after this representation, how do you do? So how do you classify? So it's actually very simple. First, you just learn k different regression. So after you learn k different regression, of course uses x as features, and then you just use a layer called Softmax by converting this k output into probability and into k after k probability. So what is the equation? Don't worry about it. Just think this is a magic layer that gives me convert this k regression tasks, k regression models, and then give me output probability of each class condition on that x. And then I'm just using this MAP rules. If you still remember the base classifier, you just use the argmax, whoever gives you the largest probability out of all the k, 1 to k, as my predicted class. So this is essentially a discriminative classifier, and that fxk hat is essentially P for that specific class K. That condition, what is that conditional probability? Yeah, so maybe more clear is P y equals to K condition on X. That's exactly that conditional probability, and which is necessary for the MAP rule to be used. Okay, so then what is this softmax layer? It's a very easy layer. It's almost look the same as the sigmoid, just a little bit different is, so if you remember what is sigmoid, in the sigmoid we have that EZ over 1 plus EZ. So this is the sigmoid, right? So, and we just, so in the softmax, you don't do that 1 plus whatever anymore. You just do exponential of a specific zi over the summation of all possible exponential to the z from 1 to k. And this gives you a normalized values, and you can treat them as probability. Essentially is P y k condition X. Is it my, yes, I'm using the K, right? All right, so so how do you use that softmax layer? So let's again keep in mind, I mean, there's K regression. So remember that. First, you have K regression tasks. And each one of them has an output, and that gives you one output. And in total, you have K output from K different regression. And this actually try to show you that that's the summation, and this is the, gives me the output is the Z1, Z2 onto ZK. And then I'm using the softmax to normalize them into probability, and this together is a softmax layer. So you can just use the softmax layer like that sigmoid logistic regression type of output layers, and then concatenate stacked with other hidden layers. In this case, I have one layer hidden layer, and then from the input I can also make two. So and normally this of course this softmax layer is used as the normally is used as the last layer when you facing a multi-class classification. And later we are going to talk about this softmax layer is actually very important, something called attention. It's based, the attention mechanism is based on the implementation of the softmax layers. All right, so now we know the softmax layer, we also know how to use it. So let's see the geometric views. So when you have the softmax layer as the last layer, and what you essentially learn is a linear separation actually of your space. Let's just use this one as a two-dimensional space. You segment your space into k different regions. So when you have k, so that just visually show you. And then what type of loss function you use, and actually very, very simple. It's almost the it's almost the same as in the sigmoid case. And again, this is also called cross entropy loss, and you actually can derive it, and the formulation it's actually the same. So in the cross entropy loss, if you still remember, that was true y. So let's actually first review what do the vector look like. So this is your y truth, right? So and then this is a k-dimensional size of vector. Your y truth is a basis vector, right? It's a one-hot representation. Only in the y true is equals to 1. All the other are equal to 0. And then your prediction are not as binary as your truth. Your prediction vector will, it's because it's normalized probability, So its summation is 1, and each one of them is from 0 to 1. So this gives you an example of y-hat, y prediction. So if you do argmax, and this will be predicted correctly. Yeah. But how do you calculate loss? From this 2. The way we calculate loss essentially is a minus k from 1 to capital K, and then the y smaller k, and then take the log the yk hat. So if you see this, because the truth, there's only one of the yk equals to 1. That's the y truth. And then this equation essentially gives you what? This equation essentially gives you y true. That specific y true is the 1, right? And then because it's 1, and all the other are 0. There's only one of them is 1, right? Essentially, this is minus log that true class. This I'm just write that true class predicted probability. And that's essentially what it is, the loss you are trying to minimize, right? Essentially. So I'm trying to minimize argmin to get whatever parameter to minimize this. And I'm trying to argmin this part, and it's equivalent to the argmax. Yes, it's correct. Sorry, I had a hiccup. So it's equivalent to, I'm trying to argmax the log y true class predicted probability. I hope this connects. All right? Yeah. So there's a W needs to be learned. By push that log to be larger. All right. So now we actually know that derivation, the loss function it's again the cross entropy loss. Now let's connect. What is the cross entropy? What is the MultiClass? The MultiClass softmax layer, the relationship to the sigmoid layer. So it's actually very easy to see. The sigmoid, the logistic binary case, is essentially a special case of our softmax representation, and that sigmoid logistic binary representation avoids to use redundant parameters. This overparameterization is because, in the end, it's because the probability sum to 1. You really don't need to calculate 2. Yeah. So just to connect the dots. Okay. So now we finished the softmax layer, and also the relationship to the sigmoid layer, and also again, even for the MultiClass case, you also has using the same cross entropy loss. Okay, so this is the second module I want to start.